want to talk about electronics from various points of view. First of all, safety. This is the most important point of view for the electronics. Safety under braking condition. To ensure safety under braking condition, Caponord 1200 is equipped with a 2-channel continental ABS braking system. The system can manage independently front brake and rear braking system. It can be switched off independently from our Aprilia traction control when the bike is at rest. And obviously, ABS system kicks in when one or both wheels lose grip under braking condition. More safety, this time under accelerating condition, Caponord 1200 has Aprilia traction control, a system that uses exactly the same software of our APRC of LSV4 and Tuono. This is really important for us because from the reliability point of view, by using the same software means to use the same structure, so the same modules of the software, and to have a specific calibration for each model. So we don't change the software from different models, but we use the same software and we fit the software with a specific calibration. So in this way the robustness of the software is higher. Every traction control calculates the slip parameter that is shown on that formula, and this parameter show how much the rear wheel is faster compared to the front one. This means that when you are accelerating from a corner, the rear wheel starts to spin, and because this parameter show how much the rear wheel is faster compared to the front one, this parameter, slip parameter, increase. The target of a traction control is to prevent from the exceeding of a predetermined slip threshold. What does it mean? This means that when the slip, because you are accelerating increase, when the slip exceeds the threshold, the maximum threshold admitted from the system reduces torque. In a standard traction control, when you achieve this point, so the maximum threshold, you don't have any more chance for further request of torque. Nothing of more. With LSV4, APRC LSV4 on model year 11, we had an idea, we think a very clever idea, we call slip control. In our system, for each setting, we have two thresholds, not one threshold, two thresholds, a lower threshold and an upper threshold. When the slip exceeds the lower threshold, in our system, with the slip control pattern, the rider has the possibility for a further request. In between these two thresholds, the rider is able to request a further percentage of slip until the upper threshold that can't be exceeded. In few words, this means that the rider has the possibility on his right hand to request more or less stay sliding. You have in your right hand this movement. This improves your sensibility to better understand how far from the limits you are. Because remember that physical law obviously can't be one. You are the rider and you are riding. What the system can do is to improve your sensibility. As we say, you are in the loop. So this is really important. By this pattern you improve safety, and if you want to push on the bike you also improve performance. The system allows 3 different settings selectable when the bike is at rest, starting from the setting number 3, the more conservative setting for low grip condition like wet condition, until the setting number 1 for high grip condition. It can actually switch it off when the bike is at rest, independent from ABS. And also the system allows a calibrating procedure in case of tire replacement, because we allow different tire brands. So if you want to change the tire, you can do it. You just need to go into the dashboard menu and select calibrate, then ride for 8 seconds in second gear at 30 km/h. When the label disappears, means that the system has correctly recognized the new rolling circumference. So you are alone able to do it. In this slide we have the general overview of the system. In blue we have the inputs of the system, and in red we have the outputs. This system needs torque because we have a torque-based system, a full red-white torque-based system. I want to remember you that we was being first in 2007 with Schiller to introduce the full rubber wire for production motorcycle, torque-based system. The system needs also both wheel speed. As I told you, you need to calculate the slip parameter, read by ABS unit and send via CAN to the engine control unit, where we have the strategies, the software for the traction control. Then the system needs the dashboard, because the dashboard is your user interface. You can set the setting of the traction, and also you have a specific lamp when the traction is in to show you that the traction is working. As I told you, when the slip exceeds the threshold, the system reduces torque. In between the two thresholds, the system reduces torque with a combination of slow torque reduction and fast torque reduction. The slow torque reduction is the most gentle way to reduce torque, because the system reduces torque by reducing the aperture of the butterfly. So it's like to have someone that is braking for you the rear. It's a very gentle system. We call it slow torque not because the movement of the butterfly is low. We call it slow because the intake aerodynamics is low. Butterflies are very fast. Only in case of sudden loss of grip, for example, for when you pass over a wet stripe, the system reacts with a fast torque reaction by reducing spark advance without cutting ignition. It's really important to do not cut ignition because the life of the catalyst. And also it's really important to use a lot of slow torque reduction. 99% of the time the torque is reduced by slow torque, because by using slow torque reduction you can leave the engine working at the stoichiometric point. This means saving fuel, so it's important. With the combination of these two torque reduction, we have a very gentle, very smooth traction control with a very fast and ready reaction when it's needed by fast torque reaction. Now it's the time to talk about electronics to improve riding pleasure. On Caponord 500 we have the Aprilia Cruise Control, a system that leaves you the possibility to select the final speed, and the system keeps constant the speed for you, so no more action on the twist grip is needed, even if the bike is in uphill or downhill condition. The system turns off automatically if the rider acts on brakes, clutch or cruise control switch. It's a very useful system, because the system helps the rider to save fuel and to reduce stress in case of long motorway journey, because the system keeps the speed for you and you can release the throttle. Here we have a general review of the system. In blue inputs and red the outputs, where the output is the cruise control torque. That means the torque needed from the system to keep constant your selected speed. Okay, until now we have talked about electronics for safety under braking condition, electronics for safety under accelerating condition, electronics to improve performance under accelerating condition, electronics to improve riding pleasure. Now is the time to talk about electronics to improve comfort and handling. Thanks to the electronics Aprilia know-how, Caponord 500 has a new and advanced semi-active suspension system. This system has two different targets, two main targets. The first one is to maximize the comfort by reducing the vertical acceleration of the chassis. Less acceleration on the chassis means less acceleration on your body, so it's more comfort. Second target of the system is to enhance the handling by providing the best setting possible of the bike. Before go more in detail on our Aprilia Dynamic Damping, I want to give you some definition. Second element is a damping element, typically an oil damper. This element deliver a negligible force at steady state, so when the suspension is not moving, but plays a crucial role in dynamic behavior of the suspension, because this element delivers a force proportional to the stroke speed of the suspension. So when the suspension is moving, this element delivers a force. When the suspension is not moving, this element doesn't deliver force. It's clear, if you are able to manage one of both elements of this suspension, you are able to control the dynamics of the bike. Electronic controlled suspension can be semi-active when the damping element is controlled in dynamic condition, and active when also the elastic element can be controlled in dynamic condition, when energy is needed from the elastic element. As I told you before, we are talking about of semi-active suspension, so suspension where the damping element is controlled in dynamic condition, and as I told you, the damping element delivers a force proportional to the stroke speed. So it's really mandatory and important to know with a very good accuracy the stroke speed of the suspension. It's really important to understand the dynamic behaviors of the suspension, because you have to control the damper that deliver a force proportional to the stroke speed. You have three different ways to measure or calculate the stroke speed of the suspension. The first one is to measure it directly. The problem is to find a stroke speed sensor. The second way is by using an accelerometer. You can fix accelerometers on moving part of the suspension. For example, 2 accelerometers for the front, that means one on the chassis and the second one on the rim, 2 on the rear, one on the chassis and the second on the rim, on the rear rim. And then, by an algebraic integration, you can calculate the stroke speed. You have two main problems with this kind of solution, by using accelerometer. The first one is that due to the algebraic integration, you need a low frequency filtering of the signal. When you filter a signal, means that you lose useful signal. So you have a loss of accuracy because you take out signal. The second problem is that this kind of solution with accelerometers are normally used on cars application, but cars has the engine elastic suspended, so the vibration transmitted from the engine to the chassis are much lower compared to the vibration transmitted from the engine to the chassis on a motorbike. Accelerometer measure the dynamic behavior of the suspension, so the acceleration of the moving part of the suspension, but also measure the vibration of the engine. So you have to filter at low frequency of the signal, and you have also to filter at high frequency of the signal. As I told you, when you filter, you take out from the signal the noise, but also a useful signal. The result is a loss of accuracy of the stroke speed information. After 4 months, 5 of testing, we rejected this solution because the loss of accuracy of the stroke speed information. And it's mandatory to know the dynamic behavior of the suspension if you want to drive the damper in the right way. The third possibility is to use a position sensor, potentiometer. In this way, by using an algebraic derivation, you can calculate the stroke speed of the suspension without a filtering needed, and this way is with a very good accuracy of the stroke speed information. So, what we do on aDD. For the front fork, we have an exclusive patent. This is the first patent of our aDD. We use a pressure sensor that measures the pressure of the volume of air that is inside the fork. As you know, there is a defined volume of air inside the fork that increases its pressure with the increasing of the suspension compression. By measuring the pressure of this volume of air, we are able to calculate in a very robust way the stroke speed of the fork. So, this solution provides a very accurate stroke speed information. We don't use accelerometer. For the rear shock, we use a potentiometer that measures the angular position of the swing arm, and as I told you before, by an algebraic derivation, you can calculate the stroke speed of the rear shock. Again, very accurate information of stroke speed of the rear shock. Both sensors are automotive. This means automotive process, production process. For us, it's really mandatory to use automotive sensor because the reliability of this sensor, because the automotive process has a target of zero defectiveness. It's really different from the consumer process, like this monitor is consumer. The target of the defectiveness is much higher compared to the automotive. Also, the electronics valves that are inside the fork and the rear shock are automotive. Million parts are produced for the car application, so the reliability of these valves are really high. Here we have a general review of the system. In blue we have the inputs and in red the outputs. The system needs the front brake information, fork stroke speed, as I told you before, shock stroke speed, both wheel speed information, read by the AVS unit and sent via CAN to the vehicle control unit. This unit is brand new and specific developed for our Aprilia Dynamic Damping and for also Aprilia Cruise Control. And also the system needs the torque rider request read by the engine control unit and sent to the vehicle control unit. We are talking about semi-active system, so the outputs of the system are the front damping, extension and compression, and the rear damping, extension and compression. So we're talking about general definition hardware. Now is the time to talk about strategies, software strategies. So how we achieve the target to improve the comfort and to enhance the handling of the bike. First of all, comfort-oriented system. There are many well-known strategies from automotive and from the literature, really many. We can notice two. The first one is the skyhook methodology. This is very well-known methodology and quite old methodology. This methodology is able to achieve the best performance comfort-oriented at low frequency of usage of this suspension. For low frequency, I mean, for example, a long wave on the road. Low frequency of movement of the suspension, long wave. Acceleration-driven damping methodology is able to achieve the best performance at mid-high frequency of usage of the suspension. Think a shorter wave, faster movement of the suspension. So this one is better for low frequency, this one is better for mid-high frequency. We mixed them. We have an exclusive patent called mix algorithm for the two-wheel application that mix these two methodologies to achieve the best performance in the whole range of frequency of usage of the suspension. This algorithm is able to mix skyhook methodology for the low frequency and acceleration-driven damping methodology for mid-high frequency of usage, to achieve the target to minimize chassis acceleration and obviously improve comfort. The second target of Aprilia Dynamic Damping is to enhance the handling of the bike. The system is able to recognize the rider maneuvers and establish a direct link with the rider and react by providing the best setting possible. And we have the extension and the lower part, the compression. When you change the clicks for the suspension, you can move from the full closed, so you close the fork, to the full open, from this one to this one. So the damping characteristic of the suspension change between the maximum and the minimum. if you want to work in between, to have a characteristic in between, you change the click with the screwdriver, and the system, the mechanical system, follows this dotted line, these characteristics. Semi-active suspension are quite similar. Semi-active valves are quite similar. You have a wider range, wider. You can move between the minimum and the maximum with this characteristic. And if you drive the electronic valve at constant current, driving an electronic valve at constant current is like to use clicks on the mechanical suspension. The semi-active suspension follows this dotted line, different dotted line. But if you need, due to your handling-oriented strategies, to follow a different characteristics in between the minimum and the maximum, you can't. We have an exclusive pattern called Map Builder. This is the third pattern of the system that allows the possibility to design. This is an academic example, not a real example, but we are able to design the characteristics that we prefer in between the minimum and the maximum. Handling-oriented strategies recognize your maneuver, like acceleration, braking, constant attitude, gas release, and react by changing the characteristic of the suspension dynamically. What does it mean? This means that this is not a system that, for example, recognizes a braking maneuver and switch to a characteristic, and when it recognizes an accelerating maneuver, switch to another characteristic. It's not a switching system. It's a system that changes dynamically the characteristic of the suspension according to your maneuver. It's a system that follows you. This means that the system doesn't need setting from you, because if you want to ride comfortable, you don't go fast, you want to ride comfortable, the system allows you a very comfortable setting, a very smooth setting. But if you want to push on the system, on the bike, the system reacts. Just to give you an example, if you are braking, and it depends from how much you brake, when you brake, the system pull up the damping on the front fork only during the transfer load of the bike. When the transfer load is over, the system releases the damping of the front fork to allow you a good grip for the front tire, because you have also to put the bike into the corner. Handling-oriented strategies, for example, if you put the bike into a chicane, on a mechanical system, comfort-oriented, you normally have a mid-low damping. And when you flip the bike from right to left or from left to right, you have an unstable movement of the bike due to the low damping of these mechanical suspensions. With our semi-active suspension system, with our handling-oriented strategies, the system allows you a mid-low damping into a chicane to achieve a good grip of the tire without an unstable movement when the bike flips from right to left or from left to right. This possibility to design a specific characteristic in between the minimum and the maximum allowable from the valves, and by changing this characteristic dynamically and continuously according to your maneuver, allow us a single map system. As I told you, it's a system that follows you. You don't need to change the map of our Aprilia Dynamic Damping. The target is the best test setting in every riding condition. Aprilia Dynamic Damping also provides, I prefer to call it a nice gadget. We have the electric preload. The system allows 4 different settings, selectable when the bike is at rest. By an electric actuator, we can change the preload of the rear shock. This is more a nice gadget than a functionality, real functionality. But we can do something of more. As I told you, we are able to measure the angle of the swing arm. And we are also able, in this way, to calculate the height of the bike. As I told you at the beginning, if you are able to change the elastic element while riding dynamically, you can call your suspension as active. With the fifth functionality that we patented, we are able to measure the height of the bike, depending from the load on the bike, and change the preload dynamically, this means in riding condition, dynamically, to achieve the task that we defined on the map of the system. With this patent, we can say to be first to introduce active suspension on motorcycles. At the end, the key factors of the system, it's a system that maximizes the comfort by reducing vertical acceleration of the chassis. It's a system that improves handling by providing the best setting in every riding condition, with a direct link with you. The system follows you. It's easy to use, single map. The system follows you, easy. We have the exclusive active mode on the rear. Before I talked about skyhook or other methodology like acceleration-driven damping. I don't want to tell you stories regarding hooks that come from the sky and keep the frame, where under the frame the wheels can go up and down without any influence on the frame. I don't want to tell you about miracle. This is not the truth. It's obvious that we are talking about telescopic suspension, and when a telescopic suspension strikes on a road irregularity, you always have a spring to win. It's obvious. You have a spring inside. What I want to tell you is that we select the best strategies, comfort-oriented, that is able to achieve the best performance in the whole range of frequency of uses of this suspension. We combined this comfort-oriented strategy with handling-oriented strategies that establish a direct link with your maneuver and follow you in riding condition. We feed these strategies with very accurate stroke speed information, with very accurate information of the dynamics behavior of the suspension, because it's mandatory. Because if this information has a loss of accuracy, will mean that the performance of the strategy will be lower. I think that tomorrow you will feel our system, starting from the morning until the end of the day, as a system that improves your comfort and especially improve the stability of the bike. That means improve the safety. This is really important for us.